Today we're going to be going over the instrumentation that is needed in order to perform atomic absorption spectroscopy or atomic emission spectroscopy. You may recall from prior lessons that we have two forms of atomic spectroscopy, the absorption, shown on the bottom here, and the emission, which is shown on the top. And in absorption, we have across a full visible spectrum, only a few lines usually that are shown that appear as black because the sample absorbed all of that light as the light passed through. On the other hand, in emission spectroscopy, if we do a wavelength scan, we see dark backgrounds everywhere except for where the sample is emitting light at the particular wavelengths as electrons transition down from an excited state to a resting state. So the question for today is, how do we go about making these measurements on a particular sample? There is one general structure that we can think of for atomic spectroscopy when designing an instrument. And the first part is that you need a source of light, which may either be an external light source, such as a lamp, or the sample itself in some cases for emission. You need a way to introduce the sample through a sample inlet, and then what's called an atomizer, which converts the sample from either a liquid state or perhaps a gaseous state into individual atoms. Let me show you what that means. So here for a copper chloride solution, what it means to atomize the sample is to go, in this case, from a solvated liquid solution to driving off the water, which very briefly would leave you with solid particles of copper chloride, and then breaking it up into its individual atoms. Each of these steps takes a lot of energy, and that is why we often work at very high temperatures for atomic spectroscopy. And the goal here is to be able to atomize the sample without ionizing it or changing its redox state. After you have the sample, you will collect the light that is passing through it or that is being emitted by it after passing through a wavelength selector, and then finally to a detection system. And we're going to talk about most of these components in more detail in the following slides. There are really three main types of atomic techniques that we categorize primarily by the method of ionization. The first is flame atomic adsorption, in which we introduce a liquid sample through a nebulizer and then pass that sample through the flame in order to detect the absorbance. There's also graphite furnace atomic adsorption, in which the sample, a liquid sample, can be placed directly into basically an oven, which is a small graphite tube, and that is then heated up to high temperatures. And again, we can collect absorbance information as light is passed through it. And finally, for emission purposes, we use an inductively coupled plasma to directly excite the atoms of the sample so greatly that they are in excited state and then emit light as the electrons relax. The temperatures differ between the two techniques, or the three techniques, with the flame and the graphite furnace being at a few thousand Kelvin, and the plasma torch being much more energetic because we have to reach that excited state for the atoms right off the bat, and is requiring 6,000 to 8,000 Kelvin, which for reference is at nearly as hot as the surface of the sun. So a lot of engineering controls go into being able to design a plasma torch that can reach that temperature without melting everything around it. So let's start with the flame ionization. And this is really a classic form of atomic adsorption spectroscopy. So whereas we have the general diagram up here at the top, down below, we have this more specific diagram for atomic adsorption spectroscopy. And you'll notice here that the radiation source has been specified to be something called a hollow cathode lamp. And I'm going to go over that in the next slide. And then we have the flame itself, which is being fed by a source of fuel and oxidants that feeds the flame and allows it to go. And then we see here's the sample inlet. So the sample comes in, gets nebulized and mixed in with the gas and oxidant, and then passed up through the flame. The light from the hollow cathode lamp passes right through the flame over to a grating, to a monochromator. Here's the slit of the monochromator. And then in this particular diagram, we happen to have a mirror in order to reflect the light so it goes conveniently horizontally. And then it passes through, in this case, a detector, which is a photomultiplier tube, which we'll discuss in more detail later in the course. All right, let's start with the burner. So the flame itself is often configured as a long flame rather than a single candle, and that's because the light in this picture would actually be coming in from this left side, pass through the flame, and then all the way over here to where the detector would be. And the reason for that is that that gives you a centimeters long path length for the sample to be absorbing light, and it gives you higher signal. As we said before, this is operating at a few 1,000 Kelvin, and that temperature can be adjusted by modulating the type of fuel and oxidant that you're using. And you might imagine that there's actually a really low yield here. So as you feed the sample into this furnace where the flame source, much of it just goes straight out to waste and never actually gets burned. And in fact, only 1 to 2% of the sample is typically burned and passed through the flame. So you definitely have lower sensitivity in this method because the vast majority of your sample is going to waste. All right, let's take a look at the light source. So this is called a hollow cathode lamp, and this is an old technology that is still used today for atomic adsorption. And the idea here is that what we want is high intensity light at exactly the wavelength that is going to excite our sample of interest. So let's say that you are trying to detect sodium in a sample of water. In that case, you would make the hollow cathode lamp shown here by stuffing a hollow cathode tube, meaning it's just literally a hollow tube made out of glass. You'd stuff it full of sodium, or perhaps more likely coat it on the inner surface of the glass tube. Then you load that into a chamber where that becomes a cathode and an electrochemical couple, where we have a cathode and an anode separated by an insulating disk, and then this whole thing is filled with an inert argon gas. High voltage is applied between the cathode and anode, and it excites the argon gas and that's in there so much that it then bombards the sodium, energizes it, and allows it to go into an excited state. And then as the sodium relaxes from its excited state to its resting state, it emits light at a precise wavelength defined by the electronic structure of the atom. So in the end, the take-home message is we can make a hollow cathode lamp for the analyte that we're specifically interested in measuring. And that way, we're exciting at exactly the right wavelength to excite our sample. So a question for you is, given how the hollow cathode lamp works, can you think of a drawback of this design if you had a sample where, say, you wanted to measure multiple analytes simultaneously, like sodium and calcium and potassium? How would you go about doing that? So you can pause the video for a minute and think about that. Okay, I'm going to assume that you've paused the video. And so here, a problem is that you would actually need to produce a hollow cathode lamp for each individual analyte separately. Okay, so if you want to measure 3 analytes at once in a single sample, you would need to be changing out the hollow cathode lamp for each one, because each one needs to be excited at a unique wavelength, and there's only one sample at a time in the hollow cathode lamp. All right, so one question is how, once light passes through the sample and some of it is absorbed, we want to be able to detect what is coming out the other side. Okay, so we're going to set what's called a monochromator to be able to select only the wavelength where we expect to see absorption, so that we can see how much light was absorbed at that wavelength. So how do we go about doing that? We use something called a monochromator, which is where light that comes in at multiple wavelengths, like white light, such as the light coming out of the flame, and the light, some of the light perhaps that is coming in from the scattered room light, it passes through, in this case as drawn here, a prism that separates it out into its various individual wavelengths. And then you can choose which wavelength passes on in order to reach the detector by putting here a barrier with a very narrow slit. The width of the slit determines the specificity of the light selection, and we call it the bandwidth. So how wide or narrow a range of wavelengths of light reaches the detector. And so that's a critical element of a monochromator design. You can either have a prism as shown here or a diffraction grating, which in the end produces a similar enough array of monochromatic light beams that we're not going to cover the difference here in this course, but it's good to be aware that there's both a prism and a grating. All right, so a question for you is, why do we even need a monochromator in this system if coming out of the hollow cathode lamp we only have one wavelength? So I want you to think about that and think about, is that true that we only have one wavelength, and where else might light be coming from? So go ahead and pause the video and think about that. All right, so I'm going to assume that you pause the video. And so to answer this question, why do we even need a monochromator? There's actually 3 other sources of light that could get to the detector if we don't have a monochromator. The first one is that the hollow cathode lamp might not emit at just one wavelength. What if it emits at more than one wavelength, such as in the spectrum for sodium that I showed you on the first slide? And so we only want to measure the absorbance at a single wavelength at a time. So we need a hollow cathode, we need a monochromator to specify which wavelengths we're looking at. Similarly, the sample itself might also emit. Perhaps it gets so excited in the flame that in addition to absorbing, it also emits a little bit at other wavelengths, and we definitely don't want to be detecting that. And then finally, as I mentioned before, stray light from the room may actually be entering the system, and we want to filter out those wavelengths as well. All right, so then the next question is, if slit width is so critical to determining the detector, what could happen if it is too high, and what could happen if it is too low? And in particular, seems like narrower slits would be good. Is there a reason that you wouldn't want a narrow slit width? So again, pause the video, take a minute to think about this, and then restart. All right, so I'll assume that you did that. So if it's too wide, what happens is that, of course, you might have too much of the other light that wasn't absorbed reaching the detector, which is going to flood you with high background on your measurement. So you won't be able to see the absorbance very well. If it's too narrow, though, not enough light is reaching the detector, and so now you won't be able to tell that anything was absorbed either, because you'll have very low sensitivity. So it's really important to use an optimal slit width, and they're often on the order of a micron or so. Yeah, or even less. All right, and so then the final question is, what might be some possible sources of background noise or interference? And so go ahead and think about that. All right, so in terms of what it could be, we might have emissions that come from the flame or the metal housing of the flame. For example, if you're trying to detect sodium, but there's sodium in the metal that the burner is made out of, you might see that showing up. So it's really important to run a blank measurement, for example, with pure water if your sample is in water, or in some other appropriate blank, and then subtract out the signal from your blank. And then also, when you make that hollow cathode lamp, who's to say that you had 100% pure sample of the analyte to put in there? And so if there's any contaminants in there, you may also be getting extra light coming out, or extra absorbance from that. So there are multiple sources of problems, and that's why it's always important to do that blank. All right, so let's move on. That's the end of the flame for now. So let's come back now and move on to the graphite furnace. This is also a form of atomic absorption. So once again, we're going to pass light through from a light source and through a sample that has been heated into an atomized state. But now, instead of using a flame to heat the sample and excite it, now we're going to use what's called a furnace. So here is a diagram of the furnace, and the key component is this bit shown here in green, which is an inner graphite tube that can handle very high temperatures up to 3000 Kelvin in this system. And then all the rest of it is a surrounding structure that allows you to apply heat radiating in from the outside. Okay, so you load your sample in here through this little port, and it goes into the center, and you can actually load a liquid sample directly into the furnace. And here's the side view of the little droplet of sample resting inside of the graphite furnace. and then we apply high heat from the outside radiatively instead of by contact in order to get a more uniform heating over the furnace. And there's also usually an inert gas passing through this furnace, such as argon, to keep you from oxidizing the material as it's heating up. So what you really need to know about this is that the high heat of the furnace, it first desolvates your sample. So again, meaning we dry it out. So you've got to drive off all that solvent molecules. Then it burns off any extraneous organics that might have been in there, contaminants in the sample. For example, let's say you're analyzing lake water or a body fluid. All the organics will get burned off at high heat. And then finally, with even higher heat, now you finally atomize the metals that you're interested in. So it's really a three-step process happening inside of that furnace. Now, imagine, where is all that burnt stuff going? Some of the burnt off organics are flowing out in a carrier gas and are removed, but some of them are going to stick to the wall. So the graphite furnace gets contaminated over time. And so again, here it's always important to perform a blank to make sure that the contamination is not passed between runs and changing the measurement. All right, so the graphite furnace has a lot better limit of detection than the flame does. Try to think about why that might be. You can pause here and think. All right, so the reason that you have better detection, a better limit of detection here, is because instead of the flame where you're burning off your sample and then it's basically getting dispersed into the surrounding air, here all the analyte is trapped in the tube. So as soon as it's atomized, it's in that space and it's accumulating at higher and higher concentration, and in the end we reach 1,000-fold greater concentration of analyte than we would have in the flame. So you would think, this is great, it's so high sensitivity, why don't we always use the furnace? But a big problem is, like I said, that surface contamination of the furnace from the organics absorbing on it and even some metals absorbing on it, and so precision can be lower in this technique. All right, so the third and final class of atomic spectroscopy is an emission spectroscopy instead of absorption. And so this here is the diagram of what is called an inductively coupled plasma torch. And it has multiple components that I'm going to walk you through. All right, so you may be asking yourself, what is this thing? All right, so again, the goal is to be able to infuse a liquid sample, desolvate it and atomize it, meaning convert it into atoms. And then in this case, we're going to use it for emission. So we have to get the atoms excited into their excited electronic state. So we need it super hot. All right, let's see how the ICP torch works. So the idea here is we need to generate a plasma, and then we need to pump our sample through it so that it can be desolvated and atomized. All right, so let's first look at how we make the plasma. And we're going to do that by sending in an inert gas that is argon usually. So here's the argon inlet being flowed in, and it flows up through this part that's labeled in green, and then continues. It looks like there's a lid here, but it actually continues on out. And then it passes through what's called an RF induction coil. So what is the RF induction coil? It's the same as the Tesla coil that you might have seen at a science museum when they're producing a lightning for you on demand, right? So we have it here in this analytical instrument, and what it does is we're creating a very high frequency fluctuating magnetic field inside of the coil. And we're creating charged particles of argon by sparking this thing with basically our small lightning spark. So now we have charged argon circulating very quickly inside, and then there's resistance to all this motion by the unionized argon, and that creates heating basically. So resistive heating from all these molecules being forced to move around in this rotating magnetic field. And the product of this is massive heating of 6,000 to 10,000 Kelvin, again, like as hot as the surface of the sun in this thing. So we've got all that going on with this inert argon gas that's being sparked. The outer argon is here just for cooling. So we don't need now to make any more plasma, but we do need to make sure that the outer layer of this thing doesn't just melt. So, so we have cooling argon flowing here just to keep everything and keep the plasma from getting to the RF induction coil. All right, so far we've made a plasma and we've kept everything from melting. Where does the sample go in? That is shown here at the bottom. So you've got your sample going in up this inner tube, which is also being pumped with argon. So your sample mixes with argon. It passes all the way up that white tube and then up into the center of that plasma torch. So that is where it now gets desolvated and atomized. Okay, so now what we have are superheated and excited atoms of our sample. So I want you to think, why do we use this method for absorbance rather than for, I'm sorry, let me start over. Why do we use this method for emission rather than for absorbance? Okay, so why is this so much better suited for emission? And you can pause and think about it. Okay, but I've actually kind of already said the answer, which is we've got it super excited. So when we think about our electronic phase, our electronic energy diagram, where we have energy here going up, you know, normally maybe this is the resting state of an electron, but this thing, all the heat from that ICP torch is going to excite us way up here. And so the vast majority of the atoms of our sample are going to be up here in this excited state. And so then they're going to come back down and emit light at that defined wavelength so that we can detect it. So it's much more likely that you're going to see emission with this technique than that you're going to see absorption. Oh, okay, and I wrote over my next question. But so this method in particular, unlike the atomic adsorption methods where we were using the hollow cathode lamp for the flame and the graphite furnace, this one is really useful for looking at multiple analytes at once. And try to think about why that would be. You can pause the video and give it a thought. All right, so this is really good for multiple analytes because you don't need an individual light source for each analyte with this emission spectroscopy method. So the sample is the light source, right? Which means if you have a sample that has 3 different analytes in it at once, you're going to detect all those emission spectra overlaid on each other, and then you can deconvolute them by mathematical analysis. In contrast, again, if you had 3 separate analytes in a sample and you wanted to do atomic adsorption spectroscopy, you would have to have 3 separate hollow cathode lamps in order to do that. Okay, so the emission is much better because you don't have to have a separate light source for each. All right, and so we can make a final comparison of these methods. Here we have the flame atomic adsorption, the graphite furnace atomic adsorption, and then our ICP torch emission spectroscopy. And then for comparison, this chart is adding on ICP torch with mass spec at the end. And you can see here sort of a rough guide of whether you would likely use it if you wanted to analyze just one element, a few, or a whole lot. And then what the sensitivity of the method is. And some are really well suited for very low concentrations if they're high sensitivity, and not so well suited sorry, the super low concentrations are down here, part per trillion, and then the higher concentrations are up higher in part per billion. Although that's still pretty low, you can really see how all of these are sensitive methods. And we can think about whether it's good for multiplexing or not, and also our sample volumes. So these are all figures of merit that you would want to consider as you were choosing between the different methods. Okay, so I'm going to stop there. And hopefully this was a useful overview of the different types of instrumentation available for atomic spectroscopy for you.